Good morning, TCAP Bio, or afternoon, or evening when you're watching this. This is our 6th video in this session of Domain 1. It's not Domain 4, it's Domain 1. We got 8 of them. So 5 down, 3 to go. So in this case, we're going to start talking about phylogeny. I'm going to turn off my music. And so phylogeny, this is that evolutionary history. So this is how we can determine relatedness. So when we talk about phylogeny, we talk about 2 types of models. The first one is being a cladogram. And so a cladogram is a diagram that groups items together based on common characteristics. So you look at determine the number of shared characteristics, arrange them with the most common possibility. And so a phylogenetic tree is a cladogram. It's a very specific type of cladogram that represents evolutionary relationship. You look at 2 types of data. Shared derived characteristics, such things like feathers. So if you were given something like feathers, you would all indicate those are all birds, right? Scales could be reptiles. Things with a vertebrae could be pretty much anything that's a vertebrate. You can also look at DNA and protein sequence. When we look at phylogenetic trees, DNA protein sequence data is much more accurate than a shared derived character. So often those shared derived characters are also homologous structures. If you remember what homologous structures are, those are those structures that have similar structure but maybe a slightly different function. So like bat's wing, cat's forelimb, dolphin's flipper. But the DNA protein sequence data is much more accurate. So here's some vertebrate phylogeny. And so if you look at the phylogeny here, you can look at common ancestry and where their common ancestor emerged. And so here's complete phylogeny of all life on Earth. Again, pretty complex. All of these in purple and pink and the green all represent different branches of life on this tree. And so when we talk about phylogenetic tree, when we're constructing them, you determine similarities among organisms. So there's a character table, which I'll have to show you here in a little bit. You arrange organisms in a tree diagram showing the simplest possible evolution. So there's different ways to interpret this. But we're also looking for maximum parsimony. And what maximum parsimony says that all else being equal, a trait is assumed to evolve only once and be present in all descendants. So this is a character table, and so we've got chimp, mouse, turtle, frog, fish, lamprey. If we go from left to right, you have the shared derived character, so opposable thumb, only in the chimp. 4-chambered heart, chimp, mouse, amniotic egg, lungs, and spinal column. So you can see down there at the bottom that lamprey would be our outgroup, and so that lamprey would be the one that was different from the rest. And so again, this will be something that I'll have to do a separate video on, or hopefully we can do in class. So when we talk about phylogenetic trees, these are hypotheses. And so what happens is more data is gathered, the relationships are continually revised, but computers can also help us. But just to kind of show you an example of one, I've got the bendaroos, as I call them. You guys may remember these from last year or not. So here's bendaroo. Down here would be the root of my tree. This is their common ancestor. And so for a while, they're all living together, and then something happens in that environment. This blue one branches off by itself, right? So if you can see here, the blue one, there was a speciation event. These 3 continue to evolve together, like for whatever reason, and then something happens, and now the yellow one branches. So we've got the blue here branched off. Hundreds of thousands of years later, the yellow, and then the purple and orange continue together, and then something happens in the environment. And so now we have this phylogenetic tree, common ancestor, common ancestor, common ancestor of all of them. So we would say is that the purple and orange have the most common or most closely related as opposed to the orange and the yellow, right? Because these ones have the most recent common ancestor. All of them go back to this original ancestor here where they all kind of merge together. The blue. The blue is the first one to branch off. And so that blue one, this may be what we call an outgroup. And so what's nice about these, regardless, however I twist this branch here, relationship stays the same. So, and I think if I had you for honors bio, we may have done something like this with a pipe cleaners. So again, those of you that learned about phylogeny in the time of COVID, we're going to have to do a little extra work. So anyways, All right, this one's pretty quick, about 4 or 5 minutes, and so we will be back in a little bit to talk more about speciation. So, again, me signing off from 102 in the heart of Tiffin, Columbia, and I'm Tiffin Southside. Have a great day.